All right, so we're going to be talking about 2012's FRQ number 6 for the BC exam. We are given this Maclaurin series, and the first part of the question A is asking us to use the ratio test. Actually, let me annotate that. The ratio test to determine the interval of convergence of the Maclaurin series for G. So, the interval of convergence I talked about in that series review video, but there is one very big specific thing I forgot to talk about when we are computing the interval of convergence that comes up in this question. So pay close attention. It's not like I will make a big deal about it or anything. All right, so the first part of this is important. We're talking about the ratio test. So I'm going to go ahead and remember to compute the ratio test. The limit as n approaches infinity is an plus 1 divided by an. So an plus 1 in this case, I'm adding 1 to the n, so I have 2n plus 1, so plus 3 total. When I'm adding that 1, I still have that 2 coefficient, over 2n, same idea here, plus 5. Now, multiplying by the reciprocal of a sub n is the same as dividing by it, so I like to do that. It's easier for me to look at the algebra of canceling. All right, so we're here, and then we have x to the 2n plus 1. Great. Let's do some canceling and grouping. So I'm going to group these guys together. I have the same coefficient. They're essentially going to turn into 1. We'll talk about that in a second. All of these parts cancel, and we're just left with x squared in there. So this is going to equal limit as n approaches infinity of x squared, which is always going to be positive, so I can get it out of the absolute values, times 2n plus 3 over 2n plus 5. This goes to 1. So we have the value of our limit equals x squared. Now, because we're using the ratio test, we know this is going to converge when x is less than 1. So that unravels to give us x is between -1 and 1. Now, what I had forgotten about was checking these endpoints. I need to see if my series converges or diverges at the endpoints to see if I need to include them in my interval of convergence. It's essentially figuring out if we have inclusive or exclusive endpoints. Now, the way to do this is plugging this value in and this value in separately back to our series. So I have that written out already for us. Let's go take a look. All right, we are here. I have gone through all the steps of plugging everything in. I plug -1 here and +1 here, looking at these values right here. Now, let's quickly simplify these. These are going to equal equals 1 to infinity. So I have -1 to the n times -1 to the 2n plus 1. So we add those. I have -1 to the 3n plus 1. And I have 2n plus 3. And then I have the same here, -1 to the n, 2n plus 3. All right, both of these are alternating versions of the harmonic series. The alternating harmonic series converges because it's alternating. So both of these converge. Cool. Which means I include the endpoints. Now, let's go back to the first part of this. No, we won't go back to the first part of this. I'll talk you through the grading because I don't want to go all the way back to the screen, and I'll just write it up here. So you have +1 for setting up the ratio, either in your limit or separately, that's fine. +1 for computing your first limit, great. Step +1 for interval, the inner, oh my gosh, the interinterval, and then +1 for considering these endpoints, and then +1 for explaining this. So you want to make sure to explain that since these are both converging, this whole interval will converge. On the guidelines for grading this, there are sentences that says when x equals -1, the series converges. When x equals -2, or when x equals +1, I'm just making up numbers now, the series converges using the alternating series test. So we could say by AST. I think being able to say a sentence like this here allows you to say, so our entire series, our entire interval of convergence includes both the -1 and the +1. All right, let's look at part B, which is slightly less complicated because we've already taken up 5 out of our 9 points. Okay, so I am looking at part B here. We are trying to figure out the Maclaurin series for G evaluated at x equals 1/2 is an alternating series whose terms decrease in absolute value to 0. The approximation for G 1/2 using the first two non-zero terms of the series is 17/120. Show that this approximation differs from 1/2 by less than 1/200. So I have pulled out this expression. It's mostly words, or no, it's not even. It's half words, half variables. But we're saying our S value up to some point n here, some specific n, in this case n equals 2, and the difference between our actual value is going to give us this remainder error. So what we're going to do here is plug everything in by using the correct colors. G of 1/2, because that's what we're trying to approximate, minus, so we have our next value here. It's going to be 17/120. Now, it's going to be less than our remainder term, which is going to be the value of the next term here. So I'm going to plug in at 1/2. So it's going to be 1/2 to the 5th over 7. So it's less than 7 times 32, which is 1/244. Cool. Show that this differs less than 100 or 1/200th. So that's less than 1/200th. That's all we're showing. So what we're basically saying is, since we're approaching that 0, each term is going to be smaller, and it's going to be smaller than, this is the maximum possible value that our x could be. It's at 1/2 here. No, it's not the maximum value. Sorry, that's the point. The value we're approximating at. My apologies. All right. AP scoring uses third term as an error bound. That's your 1 point, and then gets the error bound and compares it. You want to make sure that you have something here. You want to compute this correctly. 1/2 to the 5th. You should know 2 to the 5th off the top of your head, and then multiply by 7. This is a non-calculator question, but I trust you to be able to do this type of multiplication. If not, practice your times tables. I don't know why I'm saying that to you, but maybe it's helpful. All right, let's look at C. All right, so the last part of this is computing the first 3 non-zero terms in the general term for the Maclaurin series for G prime of x. So in the beginning part of the problem, it tells us we have this feature. G of x has derivatives of all orders. That means we can take derivatives of all these things. Now, I like to do this term by term at first, and then do the general term to figure it out. So what I'm going to do is I'm going to get a pen. G prime of x is equal to the derivative of x over 3, so 1/3 minus 3x squared over 5 plus 5/7 x to the 4th plus ... All right, now I'm taking the derivative of this term here. It's just going to be power rule because I'm taking the derivative with respect to x. N is just a variable, not a variable. N is just a number that we don't know yet. So I'm going to go ahead and compute that. So I'm going to pull that 2n plus 1 out front over 2n plus 3 x to the 2n. And we're missing one key part that I forgot to leave space for. I need an alternating bit. So the alternating bit is still going to be -1 to the n. Because when n equals 0, at this point, it's positive, so that's how I can figure out what that n should be. Now, for grading this, you get 1 point for the first 3 terms because it specifically asks for those, and 1 point for that general term there. All right, thanks.